I'm trying to create a wave. I don't think it's going too well. That doesn't look too good. But let's see what happens when I press here. There we go. Now we have our wave, which actually looks quite decent. You know, we can make it move faster. We can make it move a bit slow. Let's make sense of this. We want to talk about transverse wave. We need to start with the definition before we take a look at anything else. So the definition reads as follows. A transverse wave is a wave in which the particles of the medium vibrate at right angles to the direction of motion of the wave. This is what I want us to focus on. The particles of the medium vibrate at right angles to the direction of motion of the wave. Let's try analyzing our wave and see if the particles are indeed moving at right angles to the direction of motion of the wave. Right, so it's easy to see that our wave is moving to the right. This is where it's generated and it's moving to the right. So if our wave is moving to the right and we are saying our particles on the medium moves up and down, well, the medium is this string that we have here, or the rope, whatever you want to call it, right? If we say that the particles are moving at right angles, then they should be moving up and down. So let's go ahead and analyze and see if that is the case. So we're going to focus on these. Let's make it move a bit slow so that we can analyze with ease. Right now it's moving a bit slow. Let's focus on this green particle. Just take a look at it. The green particle is only moving down and up and down. The wave is still going to the right, but look at the green particle. The green particle only moves up and down. Even though the wave is going to the right, the particles themselves, they're not going to the right. They're only going up and down. And the wave, the disturbance is just passing through the particles. And that makes the particles to go up and down, as we can clearly see here. So now, not only have we defined transverse wave, we actually know what it means. We understand the definitions. As the wave is moving to the right, the particles are moving at right angles. They're making an angle of 90 degrees to the direction of the motion. They're moving up and down, as we can clearly see. Now that you've seen the simulation, I'm quite convinced that you know exactly what we mean when we say the particles of the medium are vibrating at right angles to the direction of motion of the wave. Now let's go and take a look at a few characteristics of a transverse wave. We have what we call the amplitude. The amplitude is the maximum displacement of a particle from its equilibrium position. Let's go ahead and take a look at our sketch and see how the amplitude looks like. So here, denoted by A, is our amplitude. We can see that it runs from the equilibrium position up until the maximum displacement. This is the amplitude. Maximum displacement of a particle from its equilibrium or rest position. And then another characteristic we can look at is the wavelength. The wavelength is the distance between two successive points that are in phase. Don't worry about what in phase means at this point. We're going to touch on that at a later stage. But wavelength is the distance between two successive points that are in phase. For instance, look at B, running from this point here up to this point. Between these 2 points, we have one complete wavelength. We have completed 1 second. And again, other 2 points that will give you a wavelength. If we concentrate on this point, then from this point to this point, we have one complete wavelength. We have completed once again. Which other 2 points can you see that are giving us a wavelength? C and F. Between C and F, we have one wavelength. We have one complete cycle. And then let's go ahead and take a look at the last one. If we take a look at E, so from this point up to this point, we have one complete wavelength. We have a wavelength between those 2 points. Let me show you what I mean by that. Right, you can clearly see that here we have half of a circle, and here we have another half. That gives us a wavelength, one complete wavelength. So right, that is what we mean when we say wavelength. In the examination, a question can ask you to calculate the wavelength, or you can be given measurements on a transverse wave like this one we have, and you need to give the wavelength. So right, that is wavelength. Let's move to trough. So trough is the lowest point on a wave. That's as easy as that. The trough is the lowest point at a wave. So for instance, this point right here, that is the lowest point, right? As our wave goes down, that is the lowest point. So that is a trough. This is another trough, and there we go. Those are our lowest point. We call them troughs. Easy to see. And then D, we have what we call crest. Crest is the opposite of a trough. It's the highest point or peak on a wave. So if we're saying that these are our troughs, then where are our crests? This is a crest, this point is a crest, and this point is a crest. It's the highest point or peak on a wave. The last aspect, equilibrium position or position of rest. It is the central line that shows the position of undisturbed string or spring. So this line here running through the wave is what we refer to as the equilibrium position or position of rest. It is the line that shows the position of undisturbed string or spring. So we need to memorize these definitions because they are usually tested in the examination. So there we go. We have our amplitude being denoted by A. This is our amplitude. And then we have a wavelength, the distance between two consecutive points that are in phase. For instance, this point is in phase with this point and they are successive. So we are going to have one wavelength. As you can see, there is one circle in between those 2 points. So they give us a wavelength. And then C, we have a trough. Trough is our lowest point right here, like we have talked about. And then crest, our highest point or peak on a wave right here. And then equilibrium position, the line that shows the position of undisturbed string or spring. This line that is dotted in our case. So there we go. Those are the basics we are interested in transverse waves. I say that we're going to talk about points being in phase and out of phase. So let's go ahead and do that. C and F are in phase, just like G and I. There are also 2 points that are in phase. So let's go ahead and take a look at C and F. We are saying that C and F are in phase, just like G and I. I want you to realize something. Between C and F, there is one wavelength. And then between G and I, there's also one wavelength, because here we have somewhat a third of a cycle, and here we have the rest. Between I and G, we have one complete wavelength. But what does the definition say? The definition says that points are in phase if those 2 points are separated by a whole number multiple of complete wavelengths. 2 points are in phase if they are separated by a whole number multiple of complete wavelengths. Let me show you what that means. Let's pay attention to this point that I'm making right now. So that point and this point, they're not in phase. Why am I saying that they're not in phase? They're not in phase because between them, we only have half of a wavelength. It's not a whole number. Half is not a whole number. So between those 2 points, we have half of a wavelength. So we cannot say that they are in phase because they are not separated by a whole number of complete wavelengths. They should be separated by one wavelength, 2, 3, 4, 5, 6, on and on, but not 2.5 and not a half. That's not a whole number. So let's go ahead and touch on the idea furthermore. Now let's take a look at these 2 points that I've denoted. Are these 2 points in phase? Are they separated by a whole number of wavelengths? Yes, they are, because here we have half of a circle and here we have another half. So between them, there is one wavelength. So those 2 points are in phase because they are separated by a whole number multiple of complete wavelengths. Right. So let's say we are interested in these 2 points. Are these 2 points in phase? No, they are not, because they are no longer separated by a whole number of wavelengths. Now we have 1.5, because this is one wavelength and this will be a half. So now they're separated by 1.5 wavelengths. So we cannot say that they are in phase because they're not separated by a whole number of wavelengths. But if we move that point and we put it here, then they're going to be in phase because they're separated by 2 wavelengths, right? This is 1 and this is 2. So those 2 points, they're now in phase because they're separated by 2 complete wavelengths, right? But let's not only concentrate on the points at the equilibrium position. Let's also concentrate on the crest and the trough. So what about this point up here? Obviously, between these 2 points, we cannot say that they are in phase because there is no whole number multiple of complete wavelengths. And then what about these 2 points right here? Are they in phase? No, they're not. We don't have a complete wavelength in between them. We don't have a whole number of complete wavelength in between them. Just like these 2 points, they're not in phase. But these 2 points, they are in phase. Why am I saying that they're in phase? They're in phase because we have one complete wavelength in between them. So we can say that they're in phase. If we move that point and put it here, then the 2 points would still be in phase because now we have 2 wavelengths in between them, and that's a whole number multiple. So that's how it goes. If there's a whole number multiple of complete wavelengths between 2 points, then they are in phase. If that condition is not met, then they're out of phase. Right. So points are out of phase if they're not separated by a whole number of points are out of phase if they're not separated by a whole number multiple of complete wavelengths. Right. So that is how we differentiate between points that are in phase and points that are out of phase. Points are not only in phase when they're close to each other like this. There are people that think they're only in phase when they're close to each other like this and they form one complete wavelength. No, they can form 2 complete wavelengths and still be in phase because it is a whole number multiple. In fact, this point is in phase with this point. Between them, there's a whole number multiple of wavelengths. Let's go ahead and prove that. So this is going to be 1 wavelength. We have 2. 3, and 4. So between those 2 points, there's a whole number multiple of complete wavelengths. So we say that they are in phase because of that. Let's talk about the period, frequency, and the wave speed. So the period, by definition, is the time taken for one complete wave pulse. We use the symbol T to denote the period. It is equals to 1 divided by F, where F is the frequency. The SI unit for period is second. And then frequency is the number of wave pulses per second. The number of wave pulses per second. And it is denoted by F, where the frequency is equals to 1 divided by the period. So if you have the frequency, you can find the period. And if you have the period, you can find the frequency. The SI unit for frequency is Hertz. And lastly, we have wave speed, denoted by V. It is the distance traveled by a point on a wave per unit time. So the equation for wave speed, we have V being equals to the frequency multiplied by the wavelength. This symbol right here is wavelength. Right, so the speed of the wave is in meters per second, the frequency is in hertz, and the wavelength is in meters. Let's go ahead and take a look at a few examples. When a string is vibrated at a frequency of 10 hertz, a transverse wave of wavelength 0.5 meters is produced. Determine the speed of the wave as it travels along the string. Let's write down the information that is given. So we know that the frequency in our case is equals to 10 hertz. We are also given the wavelength. This is said to be equals to 0.5 meters. And the question is saying, let's determine the speed denoted by V. So take a look at these three variables we have. Which equation can we use to determine the speed of the wave? We will use the speed of the wave is equals to the frequency multiplied by the wavelength. This is the approach we should always take in physics. We write down the given information and it guides us to the equation we need to use. Anyway, let's carry on. The frequency here is 10 hertz. So we're going to have 10 multiplied by the wavelength, which is 0.5. If you put that in a calculator, you'll get 5 meters per second. So there we go. The speed of the wave as it travels along the string is 5 meters per second. Let's go ahead and solve the problem that follows. Example 2. A wave with a wavelength of 1.5 meters moves past a point in 20 seconds. 60 complete waves are completed. Calculate the frequency of the waves. So let's go ahead and try answering 2.1. Let's write down the given information. The wavelength is equals to 1.5 meters. And then we have some time taken. So we have delta t being equals to 20 seconds. We have 60 complete waves. And we need to determine the frequency. So the frequency is what we're interested in. Well, in order for us to find the frequency, we can use F is equals to 1 divided by the period. But as you can see in our case, we don't have the period. So this equation is not gonna work. What other equation can we use? We can use the fact that the speed is equals to frequency multiplied by wavelength. We do have the wavelength, but we don't have the speed. So we cannot use this equation to find the frequency. So how are we going to solve this problem? We cannot use f is equals to 1 divided by t, and we cannot use the wave's speed as we don't have it. This is where we need to go back to the definition. How did we define frequency? We defined frequency as the number of complete wavelengths passing a point in 1 second. So in our equation, rather, we are told that in 20 seconds, we have 60 complete waves. We can say that the frequency is equals to the number of waves divided by the time taken. So what is the number of waves? We have 60 complete waves, and that is taking place in 20 seconds. So what is 60 divided by 20? 3 hertz. So there we go. In 1 second, we have 3 waves being completed. This is what a frequency of 3 hertz implies. 2.1. Let's go ahead and take a look at 2.2. Period of the waves. Now that we have the frequency, it becomes easy to actually determine the period of the wave. We know that the period denoted by t is equals to 1 divided by the frequency. So we're going to have 1 divided by 3 being equals to 0.33 seconds. So this is the amount of time taken to complete 1 wavelength. Time taken for 1 wavelength to pass a given point. 0.33 seconds. And the last question, 2.3, we're supposed to determine the speed of the waves. We have the frequency, which is equals to 3 hertz. We also have the wavelength. It is 1.5 meters. So we have 1.5 meters. We are interested in the speed of the waves. Well, with these 3 variables, we are just going to use the fact that the wave speed is equals to the frequency multiplied by the wavelength. Frequency is 3 hertz, wavelength is 1.5, and this will give us 4.5. So there we go. Our wave speed is 4.5 meters per second. And there we go. We have the frequency, period, and speed of the waves. Just to make emphasis, frequency is also equals to the number of waves divided by the time taken, right? Because we are interested in how many waves are passing a point in 1 second. So we can use number of waves divided by the total time taken. Let's move to the following example. So in example 3, a wave speed has a frequency of 400 hertz and a wavelength of 0.75 meters. Calculate the speed of the wave. Well, it's pretty much straightforward. Again, we have the frequency, we have the wavelength, we're looking for the wave speed. So we're going to say that the wave speed is equals to the frequency multiplied by the wavelength. So we have 400 multiplied by 0.75, which is equals to 300 meters per second. And just like that, we have answered our question. Well, this is not the last time we are doing examples on transverse waves. Here we're just trying to get familiar with the idea. We will look at longitudinal waves, and after that, solve some past exam questions. Make sure you keep watching, you don't want to miss that. Let's solve some past exam questions. The first question, how many complete waves are indicated in the sketch? So let's go ahead and find out. We have our sketch right here. There we go. We have our line of equilibrium. Now let's start counting. Let's see how many complete waves are indicated in the sketch. One complete wave it's 1 cycle. So let's go ahead and start counting. So from this point right here, if we keep going, we have 1 full cycle when we reach this point. Here we have 1 full cycle. That is 1 wave. Let's keep going. Why are we saying it's 1 wave? Maybe we can touch on that first. If you take a look, this is half a cycle and this is another half. If you add those two, you get 1 complete cycle, 1 complete wave. So that's why we're saying we have 1 wave. And then if we keep going, at this point right here, we have our second wave. Again, half a cycle, 1 complete wave. And now let's go ahead and continue counting. If we keep going, when we reach this point, we have the third wave. Half a cycle. Half and half will always give you 1 whole. So there we go. We have 3 waves. How many complete waves are indicated on the sketch? 3 complete waves. The second question, write down the letters that indicate any 2 points that are in phase. We're interested in points that are in phase. Maybe what we want to do first is to just define what it means when 2 points are in phase. Points are in phase when they have a whole number of wavelength in between them. So if between any 2 points there is 1 wavelength, they're in phase. 2 wavelength, they're in phase. 3 wavelength, they're in phase. As long as it's a whole number of wavelength in between the 2 points, then they are in phase. For instance, B and D. B and D are 2 points that are in phase. The same is true with C and E. There's 1 wavelength between C and E. So those are other 2 points that are in phase. But kid you not, between C and G, we have 2 points that are in phase because there is 1, 2 wavelength in between them. So B and D is an answer, C and G is an answer, D and F is an answer, also B and F, because from B to F we have 2 complete waves. So that's a whole number of wavelengths. So there we go. Those are points that are in phase. And then there's no in between. If 2 points are not in phase, they are out of phase. So points C and F are not in phase. They're out of phase. Point A and B, they're also out of phase because there is no whole number of wavelength in between them. For 2.2, we can just say A and C. A and C are 2 points that are out of phase. And then 2.3, we're supposed to indicate any 2 points that represent 1 wavelength. So don't get this question wrong. Any 2 successive crests will represent 1 wavelength. So B and D, from B to D, we have 1 wavelength. From D to F, we have another wavelength. And then from C to E, we have another wavelength. And the same is true with E and G. That's another wavelength. So the answer to 2.3, we can just say B and D. Between B and D, we have another wavelength. Let's go ahead and do question 3. Calculate the amplitude of the wave. From the given information, the height of the wave from the trough to the crest is 1.5 meters, and the amplitude should be half that. We know that the amplitude is the height from the rest position to the crest, or from the rest position to the trough, not from the trough to the crest. So in this case, we can say that the amplitude is equals to 1.5 divided by 2, which will be equals to 0.75 meters. So there we go. We have our amplitude, which is 0.75 meters. It's very rare that in an exam situation, you will be given the amplitude in a straightforward manner. The amplitude is 1 meter. It's very rare that you're given a situation like that. Usually, you have to calculate it. There's a bit of trickery that you have to overcome in order to find the amplitude. And then the fourth question, calculate the period of the wave. So let's go ahead and take a look at the given information. 8 waves hit the seawall in 5 seconds. So we have 8 waves hitting the seawall in 5 seconds. That is actually all the information we need to calculate the period, because we don't have the frequency in this situation. So we cannot use frequency to calculate the period. But we can say that the period T is equals to the change in time divided by the number of waves. If we use this formula, we're going to get the period. Why does this formula hold? Why is it true? The period is the amount of time taken to complete one wave. If we divide the total time by the total number of waves, we're going to find how much time it takes to complete one wave. So delta T will be equals to, the time is 5 seconds and the number of waves is 8. And I'm getting 0.625 seconds. So there we go. We have the period of the wave. Let's move to the question that follows. Question 5, calculate the frequency of the waves. If we already have the period, calculating the frequency becomes extremely easy. So the frequency will be equals to 1 divided by the period. This is 1 divided by the period, which is 0.625. So what is 1 divided by 0.625? 1.6. So we have the frequency being equals to 1.6 hertz. And there we go. We have the frequency. If you have the period, it's really easy to calculate the frequency, and vice versa. The last question, calculate the velocity of the waves. So we have the frequency, we have the period, but I don't think we can use the period to calculate the velocity. What else do we have? We have the wavelength. It's given to us in the diagram provided. Now we're looking for the velocity. Should be easy to see that the velocity will be equals to the frequency multiplied by the wavelength. The frequency is 1.6 hertz, and then the wavelength is right here. From C to E we have one wavelength, and that is 9 meters. So 1.6 multiplied by 9 meters, that is 14.4 meters per second. And just like that, we have our velocity. Transverse wave. A transverse wave is a wave in which the particles of the medium move perpendicular to the direction of motion of the wave. So that is transverse wave. Pretty much straightforward. The first question. Let's take a look at the second question. Name 2 points that are in phase. Again, by definition, if 2 points are in phase, they have a whole number of wavelength in between them. If there's one wavelength between the 2 points in phase, 2 in phase, 3 in phase, 100 in phase, as long as it's a whole number of wavelength in between the 2 points. So let's go ahead and take a look at our sketch. Between A and B, do we have a whole number of wavelength? No, we don't. Between A and C, do we have a whole number of wavelength? Let's go ahead and find out. This is one wave up to this point, and this is the second wave. So between A and C, we have 2 wavelength, 2 complete waves. So those 2 points are in phase. So the answer to 2.1, we have A and C. There's a whole number of complete waves in between the 2 points. Right, let's go to the question that follows. Name the point B. What do we call this point? That is a trough. If it was D, it would be a crest. So there we go. 2.2, that is a trough. And the 2.3, we're supposed to name the point D. Our point D is the crest. Let's move to the questions that follow. Question 3. Determine the amplitude of the wave in meters. Right, let's go ahead and take a look. Just like the question we solved previously, we are given the distance between the trough and the crest. And we know that if we are given the distance from the trough to the crest, you divide it by 2 in order to get the amplitude. So we're going to have the amplitude being equals to 20 divided by 2. This is equals to 10 centimeters. But let's pay attention to details. The question says, let's determine the amplitude of the wave in meters. So we're supposed to convert these 10 centimeters to meters. How do you convert 10 centimeters to meters? You divide by 100, because in 1 meter, there's 100 centimeters. So we're going to have 10 divided by 100, which is equals to 0.1 meters. So there we go. We have the amplitude of the wave in meters. 3.2, we need the wavelength. Take a look at this. We're given the distance from A to C. It is said to be 4 meters. We know that from A to C, we have 2 wavelengths. So from that point to this point here, we have 1 wavelength. Why do we say so? Take a look at this. This is half a circle. This is another half. So 2 halves gives you a whole, and a wave is a complete cycle. So there we go. We have 1 wavelength. And then if we keep going from this point up to C, we have another wavelength. We have a complete circle. So that 4 centimeters is representing 2 wavelengths. So what can we do in a situation like this? We can say that 2 wavelength is equals to 4 meters. Right, we're given the distance of 2 wavelengths, and it is said to be 4 meters. So obviously, we just need to divide both sides by 2. If we do that, the wavelength is equals to 2 meters. And there we go. We have the answer to 3.2. Right, so let's be aware of these type of situations in the exam. Most of the time, you're not going to be given the amplitude or the wavelength. You have to do some calculations to determine it. But anyway, stories. Question 4. 4.1, calculate the period of the wave. We are given the frequency. Obviously, if we are given the frequency, it becomes very easy to compute the period. So we're going to have the period being equals to 1 divided by frequency. This is going to be 1 divided by 0. Not 0.5, but 1.5. Our frequency is 1.5. And this will give us 0.67 seconds. So there we go. We have our period. What about the speed? Now we need the speed of the wave. We have the frequency, 1.5 hertz. We have the wavelength, 2 meters. We are looking for the speed. This is pretty much straightforward. The speed is the frequency multiplied by the wavelength. The frequency is 1.5 and the wavelength is 2 meters. This should give us 3 meters per second. As you can clearly see, our wave is moving from the west to the east. And as it is moving from the west to the east, the particles in our medium is also moving west to east. So we are going to zoom in on the longitudinal wave so you can see what I'm talking about. There's something interesting I want to show you. In front of us, we still have a longitudinal wave, but take a look at this. Okay, we can see that our wave is moving from the west to the east, if so we can say. But let's pay attention to this red particle. Take a look at it. It moves backwards, it moves forward, and then again it moves backwards. So that's the movement of particles in a longitudinal wave. They move parallel to the direction of the motion, unlike in transverse where they are moving perpendicular. Here they move parallel to the motion of the wave. But the position of the particles, they just move to the east and move back to the west. They don't move with the wave and never come back, as we can clearly see. It might look like that if you're not paying much attention. But if you pay attention, you can clearly see that the particles move to the east, move back to the west, east, west, as the wave propagates through the medium. So that is longitudinal wave. By definition, a longitudinal wave is a wave where the particles of the medium vibrate parallel to the direction of motion of the wave. But what do we call this region where particles are close to each other? And this region here where they're not closely packed. A compression is a region of high pressure in a longitudinal wave, while a rarefaction is a region of low pressure in a longitudinal wave. You can clearly see that these points or the region rather, where the particles are close to each other, we call that a compression. It's a region of high pressure, while a region of low pressure is referred to as a rarefaction, clearly indicated on our sketch. So those are some of the properties of a longitudinal wave. The same wave equation we were using with transverse wave also applies to longitudinal waves. The speed is still equals to the frequency multiplied by the wave length. A good example of a longitudinal wave is sound wave, and we are going to talk about that next. So let's go ahead and take a look. So a sound wave is an example of a longitudinal wave, as I have stated, and then vibrations in a medium in the direction of propagation create sound wave. Sound waves cannot be propagated in a vacuum. So that is the second point. That is the second thing you need to note. Speed of sounds depend on the properties of a medium. It travels faster in a medium with particles closely packed. In a solid, the speed of sound will be greater than in a liquid, and then the speed of sound in a liquid will be greater than that in a gas, because as the particles become more closely packed, the speed of sound increases. Sound waves travel faster through liquids like water than through the air because the water is denser than air. Sound waves travel faster through liquids like water than through the air because water is denser than air, obviously. And this is just another example to show that in liquids, we expect sound to travel faster than in air because the particles in a liquid are more closely packed compared to the particles in a gas. The last point, sound waves travel faster in solid than in liquid because a solid is denser than a liquid. Again, making emphasis on the relationship between speed of sound and how closely packed the particles in a medium are. The more closely packed they are, the faster the speed of sound. Characteristics of sound. The first thing we look at is the pitch. The frequency of a sound wave is what your ear understands as pitch. So if the frequency is higher, we're going to have a higher pitch. So what are we saying? We're saying that frequency is directly proportional to the pitch. As the frequency increases, the pitch increases.
Hopefully you can hear that the pitch in my voice has increased because now I'm trying to talk very fast, and this is how frequency affects the pitch. So I've increased the frequency in my sound waves and your ear is interpreting it as an increase in the pitch. So this is the relationship between frequency and the pitch. As the frequency increases, the pitch increases. Right, let's move to loudness.
The amplitude of a sound wave determines its loudness or volume. Loudness is the listener's evaluation of amplitude. A larger amplitude means a louder sound. Loudness is directly proportional to the amplitude. Loudness is measured in decibels. I'm sure you've seen this unit in electronic devices. That is the unit for loudness, decibels. Let's consolidate. We're saying that the amplitude is related to the loudness. When I talk like this, I sound louder because I have increased the amplitude of the waves I'm emitting. So this is what we mean when we say the amplitude affects the loudness. Hopefully that makes sense. Now let's talk about the tone. The tone is a measure of the quality of the sound wave. Let's go ahead and see if we understand pitch, loudness, and tone. Okay, so we have an example here. Two musical notes have the same amplitude. So amplitude is related to what? Amplitude is related to loudness, like we've talked about. But note A has twice the frequency of note B. Okay, frequency is related to pitch. In which respects will A, the sounds differ? These two notes have different frequencies, so the pitch is going to be different. The pitch of the two musical notes will be different. And then B, in which respects will their sounds be the same? They're going to be the same in terms of loudness because we have the same amplitude. So amplitude, loudness, frequency, pitch. This is a type of question you would usually expect in a multiple choice. So let's make sure that we familiarize ourselves with the characteristics of sound waves: pitch, loudness, and tone. Let's move to the following aspect. If you were to stand in an empty room with no furniture and say, hey, you would hear a follow-up saying, hey, 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 something like that, right? So that is echo. Echo is when a sound wave strikes a wall or any hard surface and is reflected back and you hear it again. So that is why in an empty room, you will hear echoes. When you say something, you will hear repetition of that same thing. It's because the sound waves hit a hard surface and then the bounce back come back to your ear and you hear it again. But in a room with furniture, there's a lot of soft materials. For instance, if you are in a living room, there's probably a couch. What else? Other soft materials. So when the sound waves strike the couch, they don't get reflected back as they would in a normal wall. So that is echo. Echoes are a result of the sound waves hitting a hard surface and being reflected back and you hear them again. Let's take a look at a few problems. A man stands between two tall buildings. When he claps his hands, he hears an echo from one building after 2 seconds and an echo from the other building after 3 seconds. Calculate the distance that the buildings are apart from each other. Take the speed of sound as 330 meters per second. So let's conceptualize. A man stands in between two buildings. So let's say that here we have the building A and here we have a building B. Let's take the first building as A. He hears an echo from A in 2 seconds. If he hears an echo in 2 seconds, it means that for the sound waves to travel from the man to A, it takes 1 second. And to travel from the building back to the man, it's another 1 second. And then now let's take a look at the man and the second building. It takes 3 seconds. So for the sound waves to travel from the man to the building is 1.5 seconds, while traveling from the second building back to the man will be another 1.5 seconds. We're just dividing the time taken by 2. 2 divided by 2 is 1. 3 divided by 2 is 1.5 seconds. So this is the first thing you have to realize when you are working with echoes. As soon as you make sense of this, you are done. You can easily solve all the problems. Again, if it takes 2 seconds for the men to receive an echo from the first building, then it takes half that for the sound waves to travel from the men to the building, and then half to travel from the building to the men, because the speed of sound is constant during the entire motion. So now what we can do is to find the distance between the men and the first building A. The distance will be equals to the speed multiplied by the time. We have the speed of sound, 330 meters per second. So this will be 330 multiplied by 1, which is 330. So we have 330 meters. The first building is 330 meters away from the man. Now let's take a look at the second building. The distance is equals to the speed multiplied by the time. The speed 330 and the time 1.5 seconds, and that is 495. So we have 495 meters. So there we go. We have the distance between the man and the first building, the distance between the man and the second building. But the question says that we must calculate the distance the two buildings are apart from each other. So this is what we are looking for. How are we gonna determine that? We're gonna say that the distance is equals to 330 plus 495, which is equals to 825 meters. Here we have the men. This is 330 and this is 495. So if we want to find the distance between A and B, we just easily add those two numbers. So there we go. That is example 1. Let's go ahead and take a look at example 2. So example 2, the speed of sound in seawater is 1,500 meters per second. A fishing boat sends signals out that are received after 20 seconds. Calculate the depth of the seabed at that position. So the depth, we are interested in the distance. Okay, so distance is what we are interested in. We have the speed of sound in seawater. So our speed is 1,500 meters per second. And we are given the time. A fishing boat sends signals out that are received after 20 seconds. So again, we have the same situation as the problem we just solved before. We are given 20 seconds for the entire motion, but we need to divide that by 2. So we're going to have 20 divided by 2. And then the distance will be speed multiplied by time, 1,500 multiplied by 10 seconds. This is 15,000 meters. And just like that, we have the depth of the seabed at that position. So right, the time you are given is very important in echoes. Most of the time, we have to divide it by 2. Not all of the time. Don't make that mistake. If a question is speaking about echoes, don't just say, I'm dividing the time by 2, and you don't even read the question thoroughly. Let's read the question thoroughly and then attempt the problem. But with that said, most of the time, we're going to have to divide by 2, but not all the time. Ultrasound is sound with a frequency that is higher than 20,000 hertz or 20 kilohertz. This is sound we cannot hear with the human ear because our range, the top of our range is 20,000 hertz. When sound is of a frequency beyond 20,000 hertz, then we cannot process that sound as humans. Right. And then the most common uses of ultrasound is to create images. The use of ultrasound to create images is based on the reflection and transmission of a wave at a boundary. When an ultrasound wave travels inside an object that is made up of different materials, part of the wave is reflected and part of it is transmitted. the reflected rays are detected and used to construct an image of the object. So that is ultrasound. And lastly, let's talk about the use of ultrasound in medicine and in the industry. So in medicine, we use it to visualize muscle and soft tissue. An example of that is during pregnancy, right? That thing they use there on the belly of the woman to see the fetus, depending on which stage of development, is ultrasound. And then lastly, to generate local heating in biological tissue, e.g. to break up kidney stones. So, well, apparently they use ultrasound to break kidney stones. I don't know much about that, but there we go. And then in the industry, ultrasonic cleaners are used to clean jewelry, lenses, and other optical parts, watches, dental instruments, surgical instruments, and industrial parts. Well, that is the use of ultrasound in medicine and in the industry. So now that we have covered all the basics, let's go ahead and solve some past exam questions. We are still doing past exam questions, but this time we are focusing on longitudinal waves. Let's go ahead and take a look. A longitudinal wave is a wave in which the particles of the medium move parallel to the propagation of the wave. The particles move parallel. In a transverse, they move perpendicular. Right, so that is longitudinal wave. The second question, name the paths labeled R and S. So let's go ahead and take a look at what's happening. A tuning fork with a frequency of 100 Hz created a sound wave as illustrated below. Here is our part R and here is our part S. Part R is a region of high pressure. A region of high pressure in a longitudinal wave, we call that a compression. So R is a compression. It's a region of high pressure. Taking a look at part S is a region of low pressure, and in a longitudinal wave we call that a rarefaction. So we have a rarefaction for part S. So there we go. Part R, compression. Part S, rarefaction. Let's carry on. Calculate the period of the wave produced. We have the frequency, so calculating the period should be an easy task. 1 divided by 100. This should be equals to 0.01 seconds. So there we go. The time taken to complete one wave is 0.01 seconds. The period. The second part of the question, quite interesting. A group of scientists on a submarine want to locate a whale. A signal generator on the submarine sends a wave signal underwater, and it is detected 3 seconds after being reflected by the whale. Obviously, the speed of sound in water is 1,450 meters per second. The question says, let's calculate how far the whale is from the submarine in kilometers. How far? We are interested in the distance. What information do we have? We have the speed of sound in water, V, which is said to be equals to 1,450 meters per second. Obviously, we need the time to say that the distance is equals to speed multiplied by time and calculate how far the whale is from the submarine. It takes 3 seconds for the waves to move from the submarine, strike the whale, and get reflected back to the submarine. But we want the distance between the submarine and the whale, so we need to take half that time. So delta T will be equals to 3 divided by 2. This is a situation that is very close to echoes. If you still remember, we did a few examples on echoes where we have to divide the time by 2. And this is one of those examples. So the distance is equals to the velocity multiplied by the time or the speed. Let me not say velocity. So in place of speed, we have 1450. That is the speed of sound in water. Water is denser than air, so the speed should be more than that in air. So 1450 multiplied by 3 divided by 2. This is equals to 2175 meters. And there we go. Hold on. The question says in kilometers, not in meters. So we actually have to divide this distance by 1000 in order to convert the meters to kilometers. So let's go ahead and do that. The distance will be equals to 2175 divided by 1000. And then our answer, rounded off to 2 decimal places, will be 2.18 kilometers. A timekeeper at an athletic competition is sitting at the finishing line of the 400-meter race and presses the stopwatch when she hears the starter pistol. Calculate how many seconds her timekeeping will deviate from the correct reading if the speed of sound in air is 340 meters per second. So let's make sense of our situation. We have a 400-meter race. Let's take this point as our starting point and here as our finishing point. So this is 400 meters. Let's read through the question statement again and make sense of the situation we have. So a timekeeper is sitting at the finishing line of the 400-meter race. So if the race is starting here, this is where the timekeeper is, at the finishing line. Okay? She presses the stopwatch when she hears the starter pistol. Calculate how many seconds the timekeeping will deviate from the correct reading if the speed of sound in air is 340 meters per second. So this is where the sound is originating, at the starting point, and the timekeeper is at the end of the 400-meter race. But we know fully well that the speed of sound in air is finite. It takes some time for it to travel through air. So how much time does it take for the speed of sound to reach the timekeeper at the finishing line of the 400-meter race? That's what we are interested in. Calculate how many seconds a timekeeping will deviate from the correct reading. So let's go ahead and calculate that. We have the distance, 400 meters. We have the speed of sound in air, 340 meters per second. We are interested in the time. So what do we do with these variables? We know that the distance is equal to the speed multiplied by the time. If we want to find the time, we can just use this equation. Or you can make delta t the subject of the formula first. But anyway, let's just go ahead and substitute. The distance, 400 meters. The velocity, 340 meters per second. And we're interested in the time. Now it's just a matter of dividing both sides by 340 meters per second. And we get 1.18 seconds. So the timekeeper will only start the timer after 1.18 seconds has passed. They are already running in 1.18 seconds. And that's the only time where the timekeeper will start the timer. So it will deviate from 1.18 seconds. So let's say maybe a person takes 10 seconds. I'm not quite sure how much time people usually take in a 400-meter race. Let's say 30 seconds. If you take 30 seconds, you'll find that the time on the stopwatch, delta t, will be equal to 30 minus 1.18 seconds. This is because the stopwatch is behind by 1.18 seconds. So if you take 30 seconds, the time recorded will actually be 30 minus 1.18 seconds. We have a sound emitted with a frequency between 23 and 54 kilohertz. And then the first question, give one word for the sound with this frequency, 23 to 54 kilohertz. So this is ultrasound. So there we go. We've just answered the first question. And the second question, give one other uses of sound with these frequencies. So what are the uses of ultrasound? We talked about that in detail in previous videos. We talked about the use of ultrasound in medicine and the use of ultrasound in the industry. In medicine, it is used to produce a scan during pregnancy. And then in the industry, it is used to clean optical equipments. There we go. Longitudinal waves, past exam questions. Here's something interesting. It actually takes 8 minutes for the light coming from the sun to reach the earth. So if the sun was to disappear all of a sudden, it will actually take 8 minutes for us to realize, because the light rays from the sun take 8 minutes to reach the earth. We've talked about transverse waves and longitudinal waves before. There's no rope between the sun and the earth, so the light is not traveling through a rope. There is no body of water. So how does the light from the sun reach the earth? That is where electromagnetic waves come in. Take a look at this interesting sketch in front of us. Really interesting if you ask me. But if I show you the magnetic field component, it even gets more interesting. Take a look at that. So what is going on here? What are you looking at? You're looking at what we call an electromagnetic wave. This is a result of accelerating charges. If you accelerate a charge, you have something like this. So this right here that you're looking at is what we call a electromagnetic wave. They don't require a medium to move. They travel through space, through vacuum. And that's what I want us to talk about. So let's go ahead and take a look. Electromagnetic radiation. It is produced by charges accelerating through space, like we've talked about before. Well, there's natural sources of electromagnetic radiation, and there's also man-made sources. The sun is an intense natural source of radiation. The reason why we are able to see is because the sun produces visible light. And then man-made sources of electromagnetic radiation include X-rays, radio waves, microwaves, and gamma rays. Let's carry on. What are the properties of electromagnetic waves? So the first bullet point, they originate from accelerating electric charges. We have already covered that. And then they propagate as electric and magnetic fields that are perpendicular to each other. This is how it looks like, just like we've covered in the introduction. And then the third point, they can travel through a vacuum. And lastly, they travel with a speed of 3 times 10 to the power 8 meters per second all the time. One last thing on the dual nature of electromagnetic radiation. Diffraction and interference shows that light behaves as a wave, while the photoelectric effect demonstrates the particle nature of light. We are going to talk about this photoelectric effect in detail in grade 12. And then diffraction was a topic in grade 11, but it's not there anymore. But anyway, stories. Electromagnetic radiation is classified into types according to the frequency and the wavelength of the wave. These types of EM radiation in the table below are in order of increasing wavelength. Let's go ahead and take a look. Gamma rays. Gamma rays, they have the smallest wavelength. As you can clearly see, it is less than 1 nanometers. Nanometers, 1 times 10 to the minus 9 meters. So gamma rays, they have a very small wavelength. And you know, if the wavelength is small, then the frequency will be very high. So gamma rays, they have the smallest wavelength and the highest frequency, followed by X-rays that are used commonly in the hospital to produce scans. So X-rays have a wavelength between 1 to 10 nanometers. That is why you don't find an X-ray machine at ShopRite, because it's very high frequency EM radiation. Gamma rays and X-rays are very dangerous, and this is the range of frequency of X-ray: 3 times 10 to the power 17 Hz to 3 times 10 to the power 19 Hz, and followed by ultraviolet light, 10 nanometers to 400 nanometers, and we have its range of frequency right there. So on and so on, followed by visible light, infrared rays, microwaves, and radio waves. There are some people that actually believe that microwaved food contains cancer. It can cause cancer because of the waves. But as you can clearly see, microwaves have a lower frequency compared to visible light that we used to see. So if microwaved food caused cancer, then we should get cancer because we can see either way, right? This is an uneducated opinion of saying that microwaved food causes cancer because of the waves coming from the microwave, hence the name. But this is actually not true, as you can clearly see. The frequency from microwaves is very low. Let's carry on. The wave equation also applies here. We have the velocity being equal to the frequency multiplied by the wavelength. But the difference is that the velocity is replaced by c, which is the speed of light. C is usually referred to as the speed of light, being 3 times 10 to the power 8 meters per second. Right, and let's talk about those units. Like I've already said, nanometers is 10 to the minus 9 meters. So if a question is saying 700 nanometers, this is the same as 700 times 10 to the minus 9 meters, right? And then we have micrometers. Micrometers times 10 to the minus 6. And then we have picometers times 10 to the minus 12. So these are the units that you will usually see in the exam, more especially nano and micrometers. It's very rare that you come across picometers, but nano and micrometers, very typical. So there we go, EM radiation. Let's recap. It is caused by accelerating charges. The wave equation applies. V is equals to frequency multiplied by wavelength. But the speed is always constant, 3 times 10 to the power 8 meters per second. And here are the units convention we need to think about in the exam situation. Let me show you using this example. So in this example, calculate the frequency of an EM wave with a wavelength of 200 nanometers. So what are we interested in? The frequency. What do we have? The wavelength. The wavelength is 200 nanometers. So that is the same as 200 times 10 to the minus 9 meters. But we also have the speed, c, which is always equal to 3 times 10 to the power 8 meters per second. So we always have the speed with EM waves. Don't forget that. So with these variables, how can you calculate the frequency? We know that the speed is equal to the frequency multiplied by the wavelength. We have the speed 3 times 10 to the power 8. The frequency is what you're interested in, and the wavelength is 200 nanometers. So that is 200 times 10 to the minus 9. All we need to do at this point is to divide both sides by 200 nanometers. So let's just go ahead and do that. So we are dividing by 200 times 10 to the minus 9. We get 1.5 times 10 to the power 15 hertz being our frequency. Frequency is still in hertz. It doesn't change. We use different EM radiations for different things. These are some of the uses of EM radiation. A question like this is usually in the exam, more especially the last question under EM radiation. What is the use of microwave? What is the use of gamma rays? So on and so on. So you need to know these uses. So let's go ahead and take a look. Gamma rays are used to sterilize medical equipment. X-rays are used to image bone structures. We all know that, hopefully. And then let's take a look at ultraviolet light. These use UV light, short for ultraviolet light, to look for flowers. As you can see, flowers stand out more clearly at this frequency. And visible light, this is used by humans to observe the world. Infrared, on the other hand, night vision, heat sensors, and laser metal cutting. Microwave ovens, obviously. And radio waves, radio and television broadcast. So yeah, you need to know some of these uses, at least one for every EM radiation. The last thing we are going to talk about is photons. So a photon is a quantum of light. Quantum is an energy packet. That is how we quantize light. We quantize light in terms of energy packets, or what we call a photon. A photon is a packet of light. The next bullet point, the energy of a photon can be calculated using the formula energy is equals to h multiplied by the frequency. But we know that the frequency, well, let me show you. We know that the speed of light is equals to frequency multiplied by wavelength. If we make frequency the subject of the formula here, we get the frequency being equals to speed of light divided by wavelength. So that is why we are saying that the energy can be calculated by h multiplied by the frequency, or the energy can be calculated by h multiplied by c divided by wavelength. We use c divided by wavelength because it is also equals to the frequency. But enough about that. You might be asking yourself, what is this h that we are talking about now? This h is what we refer to as the Planck's constant. The name Planck coming from the person who actually figured this out. So Planck's constant is equals to 6.63 times 10 to the minus 34. You don't really have to worry about the SI unit. So there we go. The energy of a photon is equals to Planck's constant multiplied by the frequency. It's easy to see that the higher the frequency of the EM radiation, the higher the energy, because they are directly proportional to each other. If you increase the frequency, the energy is going to increase, because the Planck's constant, well, it is a constant, it doesn't change. So with this information, can we calculate the energy of a photon? Let's go ahead and find out. So in example 1, calculate the energy of a photon with a frequency of 3 times 10 to the power 18 hertz. So we are interested in the energy. We have the frequency and we have Planck's constant. Even though this question says nothing about Planck's constant is indeed a constant. So we can use it to find our energy. So what are we going to do? We're going to say that the energy is equals to Planck's constant multiplied by the frequency. So Planck's constant, that is 6.63 times 10 to the minus 34, multiplied by the frequency, which is 3 times 10 to the power 18 hertz. So now I'm just gonna go ahead and put that in my calculator, and I'm getting 1.99 times 10 to the power minus 15 joules. The SI unit of energy is joules, so you should not forget that. So there we go. It's quite easy to calculate the energy of a photon if you have the frequency. Energy is equals to Planck's constant multiplied by the frequency. Here we're actually given the energy of a photon, 3.5 times 10 to the power 19 joules, and we are supposed to calculate the wavelength of this photon. So what are we given? We are given the energy. We are asked to find the wavelength of this photon. But I know that I have Planck's constant. So, right, this is where I'm at right now. So, how can we possibly solve this question? Don't forget that we have the energy being equals to Planck's constant multiplied by the frequency. Or you can calculate the energy using Planck's constant multiplied by the speed of light divided by the wavelength. Do we have the speed of light? Yes, it is a constant. C is equals to 3 times 10 to the power 8 meters per second. So I have the energy, I have Planck's constant, I have speed of light, I just want the wavelength. So I'm going to use this equation. Let's go ahead and do that. So the energy is 3.5 times 10 to the power 19. Planck's constant, that is 6.63 times 10 to the minus 34. Multiplied by the speed of light. I'm going to show you a trick. The speed of light is 3 times 10 to the power 8 meters per second. Everything divided by the wavelength. Some people, it's quite easy to see what we need to do here. Well, we can cross multiply and solve for wavelength. But you can just always switch these two values. It seems like better advice because it's a shortcut, but it always works. If you put these in the calculator first and then you cross multiply, you divide, you might end up making a mistake. Always take the approach that requires you to put things in the calculator less, because the more you put things in the calculator, the more likely you are to make a mistake. So this will be wavelength is equals to 6.63 times 10 to the minus 34 multiplied by 3 times 10 to the power 8. Everything divided by 3.5 times 10 to the power 19. So this is what I'm proposing. Instead of cross multiplying first and dividing both sides, just go from this step to this step. You are not going to lose any mark. There's no mark for mathematical manipulation in physics. The mark is for the ideas, picking the right formula, substituting, making necessary conventions, so on and so on. So if you do this, you don't have to worry. You're not going to lose any mark. So the wavelength that I'm getting here is 5.68 times 10 to the minus 45 meters. Electromagnetic radiation, past exam questions. Let's go ahead and take a look. The first question, write down 2 properties of electromagnetic waves. So what are those things that are always true for all electromagnetic waves? Well, we know that they travel with a speed of 3 times 10 to the power 8 meters per second. You just don't write 3 times 10 to the power 8 meters per second, but you write it in full. They travel with a speed of 3 times 10 to the power 8 meters per second. Apart from that, we know that they can travel through vacuum. They don't need the medium to propagate. So that's another property of electromagnetic waves. They travel through vacuum. So those are just some of the properties of electromagnetic waves. Let's go ahead and take a look at the second question. Which radiation has the highest energy? So from the information given, the table below shows an arrangement of electromagnetic radiation according to their frequencies, from radio waves to gamma rays, and we have the accompanying frequencies. So the question is saying, which radiation has the highest energy? We know that the higher the frequency, the higher the energy. And from the table, it is easy to see that gamma rays have the highest frequency. So they should have the highest energy. So the answer to question 2 is gamma rays, because they have the highest frequency. And the higher the frequency, the higher the energy. The third question, a certain radiation has energy of 1.99 times 10 to the power minus 20 joules. Identify the type of radiation associated with this energy. So we are given the energy. The question says that we must find the type of radiation associated with this energy. We are given a table of type of radiation and type of frequency. So we will use this energy that is given to calculate the frequency. And after calculating the frequency, it is just a matter of identifying in which range it belongs. What type of radiation is it originating from? So let's go ahead and take a look. So we know that the energy is equals to Planck's constant multiplied by the frequency. The energy is 1.99 times 10 to the minus 20 joules. This is equals to Planck's constant, which is 6.63 times 10 to the minus 34 multiplied by the frequency. So we're going to divide both sides by 6.63 times 10 to the minus 34. So let's just go ahead and do that real quick. And then on the right hand side, it's easy to see that this 2 will cancel out. And we're going to have the frequency being equals to 1.99 times 10 to the minus 20 divided by 6.63 times 10 to the minus 34. That is 3 times 10 to the power 13 hertz being equals to our frequency. So there we go. Now it's just a matter of figuring out in which range this frequency belongs to according to our given table. We have 3 times 10 to the power 13. So it doesn't belong to radio waves, as we can see, not microwaves, but infrared. As you can see, this is times 10 to the power 13. And infrared is ranging from 10 to the power 11 to 10 to the power 14. So 10 to the power 13 is in between the frequency of infrared. So the answer here is actually infrared. The question is saying, let's identify the type of radiation associated with this energy. It is clearly infrared. This question looks very similar to the one we just solved before. But let's go ahead and take a look and see what happens. So we're given the same exact table that shows an arrangement of electromagnetic radiation according to their frequencies. And the first question, how are electromagnetic waves generated? Well, we've talked about this before. They are generated by accelerating electric charges. If you accelerate electric charges, you get electromagnetic waves. You generate electromagnetic waves. So that is the answer to the first question. The second question, what type of electromagnetic radiation has the highest energy? We know that energy is equals to Planck's constant multiplied by the frequency. So the higher the frequency, the higher the energy. So it's just a matter of going to a table and seeing which type of radiation has the highest frequency. And clearly it is gamma rays. Gamma rays have the highest frequency with 10 to the power 18 to 10 to the power 21 frequency. So there we go. The answer to our second question is gamma rays. A certain type of electromagnetic radiation has a wavelength of 600 times 10 to the minus 10 meters. Identify the type of electromagnetic radiation by performing a calculation. I think in the previous question, we were given the energy and we calculated the frequency. Here we are given the wavelength, and we are going to do the same thing, because what we have is type of radiation and a type of frequency. So we just convert whatever we have to frequency, and then from the frequency we calculated, we're going to be able to identify the type of radiation. So let's go ahead and take a look. We know that speed in our case, denoted by C in electromagnetic waves, is equals to the frequency multiplied by the wavelength. So C, speed of light, 3 times 10 to the power 8. Don't forget, the speed of all electromagnetic waves is always 3 times 10 to the power 8 meters per second. The frequency is what we are interested in, and the wavelength, we have 600 times 10 to the minus 10 meters. Well, you can see what we need to do here. We need to divide both sides by the coefficient of frequency, which is 600 times 10 to the minus 10. 30 times 10 to the power 8 divided by 600 times 10 to the minus 10. On the right hand side, those two will cancel out. 5 times 10 to the power 15 hertz is equals to the frequency. So now it's just up to us to identify which frequency is 10 to the power 15 in our list provided. Clearly, it is ultraviolet, 10 to the power 15 to 10 to the power 16. So that's our answer to question 3, UV. So the fourth question, state one application of the type of radiation identified in question 3.4.1. Ultraviolet light can actually be used to kill bacteria. So that is just one of the application of ultraviolet light. What is meant by the term the dual nature of electromagnetic radiation? So what it means is that electromagnetic radiation behaves as both a wave and a particle. It shows characteristics of a wave and characteristics of a particle. To go deeper on that, the diffraction and interference of electromagnetic radiation shows that it behaves as a wave, and the photoelectric effect shows that it behaves as a particle. But the dual nature of electromagnetic radiation simply means that it behaves as both a wave and a particle. So that is 5.1. Let's go ahead and take a look at 5.2. So 5.2, a particle has 3.98 times 10 to the minus 13 joules of energy and has a wavelength of 5 times 10 to the minus 13 meters. The first question, 5.2.1, what is a photon? A photon is an energy packet. It's a quantum of light. That is the answer to 5.2.1. Let's go ahead and take a look at 5.2.2. What is the speed of a photon? We know that the speed of a photon, the speed of light, c, is equals to 3 times 10 to the power 8 meters per second. Nothing moves at a speed faster than that of light. And then 5.2.3, by means of a calculation, show that the above particle is a photon. How can we show that a particle is a photon? We can determine its speed and see if it is 3 times 10 to the power 8 meters per second. If it is 3 times 10 to the power 8 meters per second, then it is a photon. We have the energy of the particle, 3.98 times 10 to the minus 13 joules. We have the wavelength, and we are interested in the speed. Obviously, we have Planck's constant because it is a constant. So in order to determine the speed with these variables, we're going to say that the energy is equals to Planck's constant multiplied by the speed. Let's just put V because we cannot put C. We're not sure if it is a well, the question is saying let's show if it is indeed a photon, but let's put V, because at this point we're not sure whether it is a photon or not. Divided by V is divided by wavelength, because speed divided by wavelength is frequency. So let's go ahead and take a look. The energy, we have 3.98 times 10 to the minus 13 joules. Planck's constant, that is 6.63 times 10 to the minus 34. And then we're interested in V divided by the wavelength. The wavelength is 5 times 10 to the minus 13 meters. So let's go ahead and divide both sides by Planck's constant. So we're going to have 3.98 times 10 to the minus 13 divided by 6.63 times 10 to the minus 34, being equals to V divided by 5 times 10 to the minus 13. We divided both sides by Planck's constant. Obviously, on the right hand side, Planck's constant and what we are dividing it with will cancel out. So at this point, we can go ahead and cross multiply. If we do that, we're going to have 6.63 times 10 to the minus 34 multiplied by V, being equals to 3.98 times 10 to the minus 13 multiplied by 5 times 10 to the minus 13. We're going to divide both sides by the coefficient of V, which is Planck's constant. So V is equals to, well, let's just divide both sides at this point. So let me go ahead and divide by 6.63 times 10 to the minus 34. On the left hand side, they will cancel out, and then on the right hand side, 6.63 times 10 to the minus 34. Let me just put it in my calculator and not just assume that we're gonna get 3 times 10 to the power 8 meters per second. So I have 3.98 times 10 to the minus 13 multiplied by 5 times 10 to the minus 13 divided by 6.63 times 10 to the minus 34. I'm actually getting 2.97 times 10 to the power 8 meters per second. If we run it off to the nearest whole number, we would have 3 times 10 to the power 8 meters per second. But I think we can just leave it like that. That is 5.2.3. Let's go ahead and take a look at 5.3. So 5.3, will a photon of ultraviolet light have more energy or less energy than a photon of gamma rays? It will have less energy. It will have less energy, right? Because gamma rays has a higher frequency compared to ultraviolet light, and the higher the frequency, the higher the energy. So UV will always have less energy compared to gamma rays. Less energy, the saying, let's give a reason for our answer. We can say that gamma rays have a higher frequency compared to ultraviolet light. If you don't want to talk about frequency, you can say that gamma rays have a smaller wavelength compared to ultraviolet light. The smaller the wavelength, the higher the energy. That is 5.3. Let's go ahead and take a look at 5.4. So 5.4, name the type of electromagnetic radiation that is used to study animals at night. Well, leave a comment and tell me what the answer to 5.4 is. What do you think is the answer to 5.4? Name the type of electromagnetic radiation that has the longest wavelength. So let's go ahead and take a look. We have radio waves, microwaves, infrared, up to gamma rays. The longer the wavelength, the lower the frequency. So the answer to 5.1.1 is radio waves. They have the longest wavelength and hence the shortest or the lowest frequency, rather, not short. That is 5.1.1. Let's go ahead and take a look at 5.1.2. Name the type of electromagnetic radiation that is used in the treatment of some cancers. In radiation therapy, X-rays and gamma rays are used. They have very high energy and they can kill those cancerous cells. 5.1.3. Name the type of radiation that is used to send a signal from the remote control to the television. Infrared radiation. Infrared radiation. So actually, if you take a remote and press it, you don't see the light coming from that little bulb there in the front. But if you open your camera on your smartphone, and then you put the remote underneath and you press a button, any button on the remote, you will actually see a light coming from the remote, which you cannot see with your naked eye, but you can see through a camera. Right, just try that out and tell me how it goes. So 5.2, a photon of electromagnetic radiation has a wavelength of 400 nanometers. 5.2.1, define a photon. A photon is a quantum of light. That is a photon, quantum of light. Doesn't get easier than that. And 5.2.2, calculate the frequency of this radiation. We're given the wavelength, we are supposed to calculate the frequency. So the speed c is equals to frequency multiplied by wavelength. So if we want to calculate the frequency, we are going to have the frequency being equals to speed divided by wavelength. The speed is 3 times 10 to the power 8, while the wavelength is 400 times 10 to the minus 9. So let me just go ahead and put this in my calculator real quick. 400 nanometers. I'm getting 7.5 times 10 to the power 14 hertz as our frequency. So there we go, 5.2.2 and 5.2.3. Determine the energy of the photon of this radiation. Another easy equation, to be honest. Well, the energy is equals to Planck's constant multiplied by the frequency. We just calculated the frequency in 5.2.2, so we can go ahead and use that. Planck's constant 6.63 times 10 to the minus 34. The frequency 7.5 times 10 to the power 14. This is equals to 4.97 times 10 to the power minus 19 joules. In this video, I want us to talk about electrostatics as the study of static electricity. We have two types of charges, a positive charge and a negative charge. Let's just go through the definitions first before we can take a look at how they actually look like. So we have a positive charge and a negative charge. A positive charge originates with the removal or shortage of electrons. That is how a positive charge comes about. If you remove electrons or there's a shortage of electrons, we have a positive charge. While a negative charge, on the other hand, originates with the addition or surplus of electrons. These are very precise definitions that you need to be able to recall. And we are going to use these very definitions to conceptualize the idea of a positive charge and a negative charge. What if we don't have any shortage of electrons and at the same time we don't have a surplus of electrons? That is where a neutral object comes in. When the number of electrons is equal to the number of protons, we have a neutral object. It is neither positively charged or negatively charged. You've talked about this in grade 8. In grade 8, we talk about protons and electrons. Same is true in grade 9. We do talk about protons and electrons. Let's start with the neutral atom. When can we say that an atom is neutral? And consequently, in a larger scale, when can we say that an object is neutral? When we have equal numbers of protons and electrons. These small circles that you see with the positive signs are what we call protons. And these small circles or dots with negative signs is what we call electrons. So in our neutral atom, you can tell that we have 1, 2 protons and 1, 2 electrons. These ones without a sign, those ones are neutrons. They don't really affect our charge. So we have 1, 2 protons and 1, 2 electrons. Equal number of protons and electrons. Now let's talk about a positively charged atom. So in a positively charged atom, take a look at this. We have 1, 2, 3 protons. And electrons, we only have 1, 2. Clearly, we have more protons than we do electrons, right? We have more positive charges than we do negative charges. As a consequence, this atom is going to be positively charged because we have more protons than we do electrons. This is how a positive charge comes about. And then in the last diagram, take a look at this. We have 1, 2 protons, and electrons, we have 1, 2, 3, 4. We have an excess of 2 electrons. If we pair this proton with this electron and this proton with this electron, then we have 1 and 2 electrons with no pairs. In a case like this, we say that we have 2 electrons in excess, and we can actually calculate the charge of that atom if we know the number of electrons in excess. But we're going to touch on that later. This is another concept you should have covered in the previous grades. Like charges repel each other, and unlike charges attract each other. So let's go ahead and take a look. If you have 2 electrons, they're going to repel each other because they are like charges. And then if you have 2 protons, the same is true. They're going to repel each other because they are like charges. Electrons repel electrons, and protons repel other protons. While on the other hand, unlike charges attract each other. As you can see in this case, we have an electron and a proton, and they are attracting each other. The electron is pulling the proton towards itself, and the proton is pulling the electron towards itself. Let's move to the following concept. We're saying that if we have an excess of electrons, the atom is going to be negatively charged. But what is the amount of charge? If we have 2 electrons, what will be the amount of charge? If we have 3 electrons, what will be the amount of charge? Let's talk about the principle of charge quantization. In talking about this principle, we are going to be able to calculate the charge of an atom if we know the electrons in excess. So what does it say? The charge of an object is an integer multiple of the elementary charge. Well, let's talk about this elementary charge. What do we mean by the elementary charge? What carries charge in an atom is electrons. Electrons, they carry a charge of minus 1.6 times 10 to the minus 19 coulombs, right? What am I saying? I'm saying that they carry a charge, or QE, the elementary charge is equals to minus 1.6 times 10 to the minus 19 coulombs. This coulomb is the unit of charge. We're going to talk about it in detail at a later stage. What this principle is saying is that the charge of any object is just the number of electrons in excess multiplied by the charge of an electron. So you can see clearly that with this equation, this principle of charge quantization, we can be able to calculate the charge of any object as long as we know the number of electrons in excess. And obviously, if we're given the charge of an object, we can be able to calculate the number of electrons in excess using this very formula. So there we go. That is the principle of charge quantization. Let's go ahead and take a look at how it looks like when dealing with calculations. So take a look at this example. So the principle of charge quantization. An object has an excess charge of minus 1.92 times 10 to the minus 17 coulombs. How many excess electrons does it have? So we are given the charge of the object, right? The charge of the object is said to be equals to minus 1.92 times 10 to the minus 17 coulombs. This is the charge of an object. And the question is saying, how many excess electrons does it have? We're looking for the excess electrons. But we know fully well that the charge of an electron is equals to minus 1.6 times 10 to the minus 19 coulombs. So with this information, we should be able to find the number of electrons that are in excess in our object. How do we do that? Well, we know that the charge is equals to the number of electrons in excess multiplied by the charge of an electron. If we rearrange this, we're going to get the number of electrons in excess being equals to the charge divided by the charge of an electron, right? The charge of the object divided by the elementary charge. So in using this formula, we're going to have N being equals to the charge of our object, that is minus 1.92 times 10 to the minus 17 coulombs divided by the charge of an electron. The charge of an electron minus 1.6 times 10 to the minus 19. N is equals to 120. So we have 120 electrons in excess in this object. That is why we have a charge of minus 1.92 times 10 to the minus 17 coulombs. This is how you apply the principle of charge quantization. Let's take a look at the question that follows. So question 2, an object has a positive excess charge of 2.5 times 10 to the minus 18 coulombs. How many excess protons does it have? We're going to use the same equation, right? We will find the number of protons in excess by saying that the charge of the sphere divided by the charge of an electron. The charge of an electron is minus 1.6 times 10 to the minus 19. And that of a proton is plus 1.6 times 10 to the minus 19. So in this equation, we would have 2.5 times 10 to the minus 18. This object is positively charged, so it has an excess of protons or a deficient of electrons. So we're going to have 2.5 times 10 to the minus 18 divided by the charge of a proton because it has protons in excess. The charge of a proton is 1.6 times 10 to the minus 19. Don't forget that of an electron is minus 1.6 times 10 to the minus 19, and that of a proton is plus 1.6 times 10 to the minus 19. This is about 96 protons. We need the number of protons or electrons to be a whole number. We cannot have a fraction because we cannot have an electron. So this object right here has an excess of 96 protons. The last question, an object has an excess of 200 electrons. What is the total excess charge on the object in coulombs? Well, we have the number of electrons. We are looking for the charge, but we do know the charge of an electron, the elementary charge. So how do we answer this question? Well, still the same principle, quantization of charge. We have Q being equals to N multiplied by the elementary charge. So what is N? N is the number of electrons in excess. In our case, 200. And the Q is the elementary charge of an electron. So we have minus 1.6 times 10 to the minus 19. This is equals to minus 3.2 times 10 to the minus 17 coulombs. So there we go. That will be the total excess charge of an object with an excess of 200 electrons. This is how you apply the principle of quantization of charge. I did say that we are going to talk about these columns in detail. So let's go ahead and take a look at that. So as you've seen, charge is measured in units called coulombs. We know that one electron has a charge of minus 1.6 times 10 to the minus 19 coulombs. So one coulomb of charge involves a lot of electrons. More than a billion, more than a trillion. Actually, more than a billion, right? To have one coulomb of charge, you need more than a billion of electrons. So you can agree with me that a coulomb of charge is a very large charge, right? If it requires a billion of electrons, well, way more than a billion of electrons. So in electrostatics, as a consequence, we often work with charge in micro coulombs, right? This is the sign for 1 micro coulomb, right? You will need to remember this. Usually in the examination, charges are given in terms of micro coulombs or nano coulombs. So 1 micro coulomb is equals to 1 times 10 to the minus 6. And then 1 nano coulomb is equals to 1 times 10 to the minus 9. So as soon as you see micro, just know that is times 10 to the minus 6. And then as soon as you see nano, just know that it is times 10 to the minus 9. We talked about the principle of charge quantization. Let's talk about the law of conservation of charge. So the algebraic sum of the charges remains constant in a closed system. The algebraic sum of the charges remains constant in a closed system. So this is the law of conservation of charge. So if we have two spheres, A and B, and you let these two spheres touch, right? You let them touch, and after that, you separate them. What will be the new charge on the spheres? When they touch, there is an exchange or there is sharing of electrons. If A has more electrons, it will give B some of its electrons, so that after they're separated, they have equal number of electrons. The same is true. If B has more electrons than A, then it will give A some of its electrons, so that after they're separated, they have equal number of electrons. So the formula we use for the law of conservation of charge, or if we want to find the charge on two spheres after we let them touch and separate them, we use Q nu. We use Q nu is equals to Q1 plus Q2 divided by 2. You just simply add the two charges and divide them by 2. The law of conservation of charge. Let's take a look at this example. Two identical insulated spheres have different charges. Sphere 1 has a charge of minus 9.6 times 10 to the minus 18 coulombs. And then sphere 2 has an excess of 70 electrons. If the two spheres are brought into contact and then separated, what charge will each have? Okay, so we are looking for Q nu. We know fully well that Q nu is equals to Q1 plus Q2 divided by 2. So we have sphere 1 and sphere 2, right? Sphere 1 has a charge of minus 9.6 times 10 to the minus 18 coulombs. So no problem there whatsoever. We can just go ahead and substitute that in place of Q1. Let's take a look at sphere 2. Sphere 2, we are not given the charge. We are given the number of electrons in excess. So we have to calculate the charge ourselves, right? Because we know that if we have the number of electrons in excess, we can calculate the charge using the principle of charge quantization. So let's go ahead and do that. For the charge, so the charge of sphere 2 will be equals to the number of electrons it has in excess multiplied by the charge of an electron. So how many electrons does it have in excess? It has 70 electrons, and the charge of an electron is minus 1.6 times 10 to the minus 19 coulombs. One electron carries a charge of minus 1.6 times 10 to the minus 19. So if a sphere has 70 electrons, you just multiply that by the charge of one electron. This is equals to minus 1.12 actually times 10 to the minus 17 coulombs. So you can see here we are using the law of conservation of charge and the principle of charge quantization at the same time. Okay, so we have Q1 and now we have Q2. We can go ahead and substitute in order to find the charge that each sphere will have after separation. So let me just drag this to the side. Let me put it somewhere there. Right. So Q1, the charge on the first sphere, that is minus 9.6 times 10 to the minus 18, plus the charge on the second sphere, we have minus 1.12 times 10 to the minus 17. Everything divided by 2. The new charge on each sphere will be minus 1.04 times 10 to the minus 17 coulombs. So this will be the new charge on each sphere. They are going to have the same charge. Here we go. 15 March 2024. This is the common test for last year's exam. Let's go ahead and take a look and see how we're supposed to answer these questions. So the first question 1.1, multiple choice. Let's go ahead and take a look. We have 1.1. So the diagram below shows a transverse wave. Each block represents a 1 meter height and a 1 meter width. The amplitude and wavelength of the wave above are. Okay, let's start with the amplitude. So from here, let me just increase the width of my pen. From here to here should be the amplitude, right? The maximum displacement from rest position. So how many square blocks do we have? We have 1, 2, right? So clearly that should be 2 meters. So the amplitude is 2 meters. That is easy to see. So we are only looking at option A and C. Now let's figure out the wavelength. So the wavelength will be from this point to this point. So we need to calculate the number of blocks. So that is going to be 1, 2, 3, 4, 5, 6, right? 7, 8, 9, 10, 11, 12. And then we know that one block represents 1 meter. So the wavelength would be 12 meters. So the answer to 1.1 is actually A. The amplitude is 2 meters and the wavelength is 12 meters. So there we go. We have A. Let's go ahead and take a look at 1.2. So 1.2, the sound with the frequency ranging from 20 Hz to 20,000 Hz, which can be heard by the human ear, is known as the audible range. So the answer to 1.2 is B. So that is just a definition. I don't think there's any need to explain that. And then 1.3, which one of the following electromagnetic radiations has the highest penetrating ability? So highest penetrating ability, we're talking about the highest frequency or the smallest wavelength. Between these four that we have, the electromagnetic radiation with the highest frequency is gamma rays. So the answer to 1.3 is actually D. Right. And then 1.4, a sphere below carries a charge of plus 2 microcoulombs. And then the question is saying the sphere acquired a charge by gaining electrons, losing electrons, so on and so on. So let's go ahead and see which option makes sense. So electrons is what carries charge. If a sphere is positive, it has lost electrons, right? That is why it is positive. And then if it is negative, it has gained electrons. because it is electrons that carries charge. So let's calculate the number of electrons this sphere has in excess in order to have a charge of plus 2 microcoulombs. So the charge, we know fully well that it is equals to the number of electrons multiplied by the charge of an electron. So what is the charge? 2 microcoulombs. So we have 2 times 10 to the minus 6. We're interested in the number of electrons that the sphere has lost. What is the charge of an electron? Well, minus 1.6 times 10 to the minus 19. So we're going to have 2 times 10 to the minus 6 divided by 1.6 times 10 to the minus 9 to the minus 19, and that is giving me, well, minus 1.25 times 10 to the power 13. But we're talking about the number of electrons. We cannot have negative number of items, so we can just negate that minus sign. So which option corresponds with 1.25 times 10 to the power 13? That is option B. So there we go. We have the answer to 1.4. Let's go ahead and take a look at 1.5. So 1.5, the unit of measurement of potential difference in volts is equivalent to. Okay, let's take a look. So we know that the voltage or the potential difference can be calculated using I multiplied by R, of which the SI unit is going to be volts, right? But there's another way that we can use to calculate the potential difference. We see that the potential difference is equals to the work done per unit charge. So the SI unit for work is joules, and the SI unit for charge is coulomb, as you know. And then we can rewrite this SI unit as joules multiplied by coulomb to the minus 1, right? It's the same as saying joules divided by coulomb. So which option corresponds with that? Let's take a look. It looks like that is option A. So the answer to 1.5 is A for that reason. So that was question 1. Let's take a look at question 2. So question 2, a teacher uses a spring to generate 2 pulses A and B. The 2 pulses move towards each other along a spring and meet at point P, as shown in the sketch below. 2.1, define the term transverse pulse. A transverse pulse is a disturbance where the particles of the medium move perpendicular to the direction in which the pulse is moving. Obviously, instead of perpendicular, you can say it moves at right angles. That is also acceptable, right? So that is 2.1. The particles in the medium are moving perpendicular to the direction of motion of the pulse. 2.1. Let's take a look at 2.2. Write down the term for the type of interference that occurs when the 2 pulses meet at P. So A, the disturbance is above the equilibrium, and in B it is below the equilibrium. So we are going to have what we call a destructive interference, right? So that is the answer to 2.3. If they were facing each other, like something like this, or something like this, then we would have a constructive interference. But because they are pointing in opposite directions, we're going to have destructive interference. And then 2.3, calculate the amplitude of the pulse that forms when the 2 pulses meet at point P. Show your calculation. So the amplitude will be equals to, what is the amplitude of A? 20 millimeters. And then plus the amplitude of B. But because it's below the equilibrium, we're going to say minus 10. And then this is equals to 10 millimeters. So there we go. That is the amplitude when the 2 pulses meet at P. What about 2.4? Write down the term for the principle you applied in question 2.3 above. That is the principle of superposition, right? Superposition. So most of the time when the question is talking about a principle in pulses, the answer is superposition, right? It is the principle of superposition that you're talking about. Okay, what about 2.5? 2.5, how do the speeds of the 2 pulses compare? write only a greater than, or A greater than B, B greater than A, or A equal to B. Explain your answer. A equal to B. A equal to B. Why are we saying so? The two pulses are moving in the same medium, and it is the type of medium that controls the speed. The speed depends on the type of medium. So if they're moving on the same medium, then they're going to have the same speed. Okay. Question 3. The diagram below represents a wave, a water wave moving from left to right. The period of the wave below is 2 seconds. And then 3.1.1, what type of wave is a water wave? We can clearly see that this is a transverse wave, right? So the answer to 3.1.1 is transverse wave. And then 3.1.2, write down the amplitude of a wave. Okay, so let's take a look. We know that amplitude is from equilibrium to maximum displacement, right? But this 3 meters is from the trough, so to say, up there to the crest. So how do we find the amplitude in this case? We say that the amplitude is equals to 3 meters divided by 2, which is equals to 1.5 meters. So there we go. 3.1.2, the amplitude is 1.5 meters. Let's take a look at 3.1.3. 3.1.3, define the term wavelength. Wavelength is the distance between two successive points that are in phase, right? It is the distance between two successive points that are in phase. You're going to see what that actually means when we answer 3.1.4. It says, determine the wavelength of the wave. Okay, let's take a look and see how we can answer this question. So we are given some, let me just take my ruler to the other side. We are given some distance here of 28 meters, right? But then we need to figure out how many waves are in that 28 meters. That's what we need to figure out. So from this point up to this point, it's one wave, right? It's one wavelength, because one wavelength forms one complete cycle. You can see that this forms one complete cycle, right? And then let's keep going and see how many wavelengths we have in that distance that is given. And then from here up to here, it's a half, right? And then this part here forms a quarter. So this part forms a quarter. So how many wavelengths do we have in that 28 meters? We have one plus 0.5 plus 0.25, right? We have that quarter at this point. So what does that give us? That gives us 1.75 wavelength. So the 28 meters is equals to 1.75 wavelength. So what is the wavelength of the wave? Now we just need to divide both sides by 1.75. So let's just go ahead and do that. So 28 divided by 1.75, that is 16. So the wavelength is 16 meters. There we go. Let's take a look at 3.1.5. Give 2 points, give 2 pairs of points on the wave, on the waveform above that are in phase, right? 2 pairs of points on the waveform above that are in phase. So we need to know the definition of in phase. 2 points are in phase if they have a whole number of wavelengths between them. That's when we say that points are in phase. So let's go ahead and see which points have a whole number of wavelength between them. So take a look at A and E, right? Between A and E, there is one wavelength. So we can see that A and E are 2 points that are in phase. Take a look at D and F, right? 2 consecutive troughs. We can also see that D, F are 2 points that are in phase, as they have a whole number of wavelengths in between them. 3.1.5. Let's take a look at 3.1.6. So we are supposed to calculate the frequency of the wave. Well, what information do we have? We are given the period in the question statement, right? The period is said to be 2 seconds. So frequency is equals to 1 over t, which is the period. So this is 1 over 2, which will give us 0.5 hertz, right? And then B, we're looking for the speed of the wave. So now we have the frequency, we have the wavelength, we are looking for the speed, right? So we know fully well that the speed is equals to the frequency multiplied by the wavelength. The frequency is 0.5 hertz and the wavelength is 16 meters. So we have 0.5 multiplied by 16, which is 8 meters per second. 3.1.6. Let's take a look at 3.2. So 3.2, sound navigation and ranging. Sonar is the technology used to determine the depth of the ocean. A sound wave signal is sent from the ship and then the reflected wave is detected after 5 seconds. The speed of sound waves in seawater is 1,500 meters per second. Calculate how deep is the ocean directly below the ship. Give your answer in kilometers. Well, this question is sort of simplified for us because we have this sketch which shows us what we need to do. So take a look at this. A sound wave signal is sent from the ship and the reflected wave is detected after 5 seconds. So what does that mean? Well, the speed of sound in water is not going to change, right, during the time the wave is sent and received. So if the entire journey takes 5 seconds, then for the sound wave to travel from the ship to the ocean bed, it would take half that, which is 2.5 seconds. And then to go from the seabed back to the ship, it would take another 2.5 seconds, right? So in order for us to calculate the depth, that distance, we can say, well, we have the time, which is 2.5 seconds, and we actually have the speed of sound waves in water, which is 1,500 meters per second. And what are we looking for? Calculate how deep is the ocean. So we're looking for the distance, right? So we're gonna have the distance as our unknown variable, or the displacement, depending on what you are using. So we can say that delta x is equals to v multiplied by delta t, right? So delta x will be equals to the speed, well, the velocity, which is 1,500. Well, the speed, the equation says the speed, multiplied by the time, which is 2.5 seconds. And then when I put that in my calculator, I'm getting 3,750 meters. The question says it should be in kilometers, so we need to divide that by 1,000, and we're gonna get 3.75 kilometers, right? 3.2. Let's take a look at 3.3. So 3.3, sound waves with frequency higher than 20,000 hertz up to about 100,000 hertz are often used in medical industry. Write down the scientific term for the underlined words. Well, that is ultrasound, okay? Sounds with frequency ranging from 20,000 hertz to 100,000 hertz. So the answer to 3.3.1 is ultrasound. But what about 3.3.2? State and describe the medical application of the sound described by the underlined words. Well, that is just theory, so I'm gonna let you guys figure that out. Let's do question 4. So question 4, the types of electromagnetic radiation are arranged according to frequency in the table below. 4.1, what type of electromagnetic radiation has longest wavelength? So if you have the longest wavelength, you will have the lowest frequency. So in the table given, which electromagnetic radiation has the lowest frequency is radio waves, right? You can see that the frequency ranges from 10 to the 5 to 10 to the 10, which is the lowest in the table that we have. So we have radio waves, as the answer to 4.1. So 4.1, radio waves. Let's take a look at 4.2. So 4.2, explain the answer to question 4.1. Well, I just explained that the longer the wavelength, the lower the frequency. A radio wave clearly has the lowest frequency in the table given. Okay. 4.3.1, an electromagnetic radiation wave has a wavelength of 1.2 times 10 to the minus 4 meters. Identify the type of electromagnetic radiation by performing a calculation. So we are given the wavelength of the electromagnetic wave. In the table, we have the frequency. So we need to calculate the frequency using this wavelength in order for us to identify the electromagnetic wave. So in doing that, the frequency is equals to C over wavelength. So we're going to have 3 times 10 to the power 8 divided by 1.2 times 10 to the minus 4. Okay, and then this is equals to 2.5 times 10 to the power 12. So let's go ahead and identify that. Clearly, 10 to the power 12 is between 10 to the power 11 and 10 to the power 14. So it means that the electromagnetic wave is infrared. So there we go, infrared. That is 4.3.1. Let's take a look at 4.3.2. 4.3.2, calculate the amount of energy that a photon of the wave identified in question 4.3.1 has. So the energy is equals to Planck's constant multiplied by the frequency. So we're going to have, that is a constant, so it's just 6.63 times 10 to the minus 34 multiplied by 2.5 times 10 to the power 12. And then when I put that in my calculator, I'm getting 1.66 times 10 to the minus 21 joules. There we go. And then 4.3.3, state one application of the type of radiation identified in question 4.3.1. So, like I've already said, 4.3.1, the answer is infrared. So what are the applications of infrared? I'm going to leave that to you. Question 5. Two identical metal spheres A and B are suspended on long silk threads as shown in the diagram below. The spheres carries charges plus 6 nanocoulombs and minus 2 nanocoulombs respectively. 5.1, state the principle of charge quantization. All charges in the universe consist of an integer multiple of the charge on one electron. That is to say, Q is equals to the number of electrons multiplied by the charge of an electron. And then 5.2, which sphere A or B has excess electrons? It should be easy to see that it is sphere B that has excess electrons, as it is negative, right? Electrons are what carries charge and they are negative. And then sphere A would have an excess of protons or a deficit of electrons. Okay, 5.3, calculate the number of electrons on the sphere identified in question 5.2. So in 5.2, we said it is sphere B that is an excess of electrons. So let's go ahead and calculate the number of excess electrons that it has. So Q is equals to N multiplied by the charge of an electron. So we're going to have minus 2 times 10 to the minus 9, meaning equals to N multiplied by minus 1.6 times 10 to the minus 19. So we divide both sides by minus 1.6 times 10 to the minus 19, and we get 1.25 times 10 to the power 10 electrons. So there we go. And 5.4, the spheres are brought into contact and then separated. State the principle of conservation of charge. The net charge of an isolated system remains constant during any physical process. But what does that actually mean? you'll see that in 5.4.3. So that is 5.4.1. What about 5.4.2? Which sphere gains electrons when the two spheres come into contact? This is quite an easy one because A is positive and B is negative. So A is going to gain some electrons from B. It would be a bit tricky if A was also negative. But since A is positive and B is negative, A will gain electrons from B. That is quite easy to determine. Right, so the answer to 5.4.2 is A. What about 5.4.3? Calculate how many electrons are transferred from one sphere to the other when they come into contact. Okay, there we go. So the first thing that we need to do is calculate Q nu, right? The charge that the two spheres are going to have after contact. We're going to have Q nu being equal to QA plus QB in our context divided by 2. So this is 6 times 10 to the minus 9 plus minus 2 times 10 to the minus 9 divided by 2. Okay, that will give us 4, and then we're going to divide 4 by 2. We're going to get 2 times 10 to the minus 9 coulombs. That is the new charge on the two spheres. But that's not what we're looking for. We're looking for the number of electrons that are transferred. So in order for us to do that, we have Q new minus Q old being equals to N multiplied by the number of electrons. So Q new, we've calculated it, right? So there shouldn't be any confusion there. But what about Q old? What do we substitute? Do we substitute QA or do we substitute QB in place of Q old? Well, whether you substitute QA or you substitute QB, which will end up having the same answer. So let's go ahead and just substitute QB. If we do that, we're going to have 2 times 10 to the minus 9. That is Q new, right? Minus Q old, which is minus 2 times 10 to the minus 9. This is equals to N multiplied by the charge of an electron, which is minus 1.6 times 10 to the minus 19. So 2 minus 2, that is going to be 4 times 10 to the minus 9, being equals to N multiplied by the charge of an electron, minus 1.6 times 10 to the minus 19. Okay, so we're going to divide both sides by minus 1.6 times 10 to the minus 19, and we're going to get 2.5 times 10 to the power 10 electrons, 5.4.3. Okay, let's do question 6. The circuit diagram below consists of a battery, switch, and ammeter, right, and a glowing light, as we can clearly see. They're connected in series. Let's take a look at what is happening. 6.1.1, we're supposed to define the term potential difference. Is the energy transferred per unit electric charge in a conductor? Is the energy transferred per unit electric charge in a conductor? And then electric current, 6.1.2, rate of flow of charge. Let's take a look at 6.2. So 6.2, the reading on ammeter A is 0.4 ampere. So we have 0.4 ampere. Okay. So 0.4. Right. And then 432 joules of energy is transferred to a light bulb in 3 minutes. Calculate the reading on V. Usually we would just say V is equals to I multiplied by R. But the problem in this case, we don't have the resistance, so we can't use that. Another option that we have is V is equals to the work done per unit charge, right? So can we calculate Q? Do we have the work done? Yes, we have. We're given 432 joules. So take a look at this. We have V being equals to 432 joules divided by the charge. So what this question actually wants us to do is to calculate the charge, because as soon as we have the charge, it should be easy to calculate the reading on voltmeter V. So what information are we given? We are given the current and we are given the time. Remember the definition. Current is the rate of flow of charge. So what does that mean? It means that I is equals to Q divided by the change in time. That's what we mean when you say current is the rate of flow of charge. So the current is 0.4 ampere. The charge is what we're looking for, that is Q. And then delta T is 3 minutes. But we know fully well that in physics, the unit that we use for time is seconds. So we're going to have 3 multiplied by 60. And then now we cross multiply. We're going to get Q being equals to 72 coulombs. So V will be equals to 432 divided by 72, which will give us 6 volts. There we go. The distance between any two consecutive points that vibrate in phase on a wave is the wavelength, right? So 1.1, our answer here is going to be B, right? Because the distance between any two consecutive points that vibrate in phase is wavelength, right? And then off to 1.2, a wave moves past a fixed point at a speed of x meters per second. If the speed of the wave stays the same and the frequency of the wave doubles, then the wavelength of the wave will, A we have half, double, remain the same, and increase fourfold, right? So here, let's conceptualize, right? We know that we have V being equals to frequency multiplied by wavelength. So it is said that the frequency has been doubled, right? But then the velocity or the speed stayed the same. So what happened to wavelength, right? So let's say our initial frequency was 2 hertz, right? And then our wavelength was 2 meters. So V would be 2 multiplied by 2, which is equals to 4 meters per second, right? But then now it is being said that the frequency has been doubled, but the velocity remains the same, right? So if the frequency is doubled, then we're going to have V being equals to, so instead of 2, we're going to have 4 hertz, right? And then multiply by, we need V to still be 4 meters per second, right? So the wavelength now has to be 1 meters, so that the velocity remains being 4 meters per second. So you can see it with this illustration that if we double the frequency and you want the velocity to stay the same, you have to halve the wavelength, because here we had a wavelength of 2 meters to get a speed of 4 meters per second. But then now that we have doubled the frequency, we only need a wavelength of 1 meter, right? So that's how it works. This might be a bit challenging, but then if you put some thought into it, you will realize that it's not too complicated. And then now we have 1.3. 1.3 saying that the diagram below represents two sound waves, A and B. Which one of the following combinations that compares the frequency and loudness of A and B is correct? Let's look at option A. It is saying that the frequency of A is greater than that of B, right? So let's go on our sketch and see if that is true. So from here to here, we have one completed wavelength. And then from here to here, we have one completed wavelength. So if we assume that on the x-axis we have time, then that will tell us that the period of A and B is the same. And then if the period of A and B is the same, then the frequency should be the same. So now the only options we're looking at is option C and option D, because they're saying that the frequency of A and B, they are the same, right? And then let's look at the loudness, because that's the other criteria we have. Option C says that the loudness of sound wave A is greater than that of B, right? What is loudness related to? Loudness is related to the amplitude. We can see that the amplitude of B is greater than that of A. So our answer here for 1.3 is actually D, because the frequency of A is the same as the frequency of B. But then the loudness of A is less than the loudness of B because of the amplitude. Sound wave B has a higher amplitude. And now off to 1.4. So we have 1.4 here, saying that doctors use certain equipment to check on the health of unborn babies. This equipment uses, we know fully well that this equipment uses ultrasound, right? So our answer for 1.4 is going to be option C. A pulse is a single disturbance in a medium. A pulse is a single disturbance in a medium. It doesn't get easier than that, right? So that's the answer for 2.1. A pulse is a single disturbance in a medium. And now let's move to 2.2 and see what we can do here. So the diagram below shows two pulses, L and M, right? As we can clearly see on the left hand side, right? We have pulses L and M traveling in opposite directions in a row. The amplitude of pulse L is unknown and that of pulse M is 7 centimeters. And then the two pulses, they meet at point X. Point X is right here, right? And the resulting amplitude is shown below, right? We have a resulting amplitude of 4 centimeters. And then the question that follows, 2.2.1, what type of interference takes place at X? What type of interference takes place at X? So let's just cover the basics, right? If we have two pulses, one being above rest position and the other one being below rest position, then they interfere destructively, right? So we have what we call destructive interference, right? That happens all the time when we have two pulses, one being above equilibrium and one being below equilibrium, right? And then if we have two pulses both being above the line of equilibrium, then we're going to experience constructive interference, right? We're going to experience constructive interference, right? But then as you can see here on the example we have two pulses, one being above the equilibrium and one being below the equilibrium. So the type of interference that is going to take place in 2.2.1 is going to be destructive interference, right? So our answer for this question will be destructive interference. And then now let's do 2.2. So 2.2.2 is saying that why is it possible to apply the principle of superposition at X, right? So we can only apply the principle of superposition when two pulses occupy the same space at the same time, right? So that's the condition we have for the principle of superposition. The two pulses occupy the same place at the same time, right? And then let's move to 2.2.3. So 2.2.3 is saying let's determine the amplitude of L, right? We're given the amplitude of M and the resultant amplitude after they meet, right? And we know that the resultant amplitude will be equals to the amplitude of L plus the amplitude of M. The resultant amplitude will be minus 4, right? Why are we putting a minus sign? We put in a minus sign because the resultant is below equilibrium, right? And that will be equals to the amplitude of L and then plus the amplitude of M. The amplitude of M is also below the position of equilibrium, right? So we're going to substitute it with a negative sign. So we're going to have minus 7. So if we take minus 7 to the left hand side, we're going to have minus 4 plus 7 is equals to the amplitude of L. So 3 centimeters is equals to the amplitude of L, right? And just like that, we've determined the amplitude of L. And now 2.2.4. 2.2.4 is saying that in which direction does pulse M move after the two pulses pass each other, right? Either to the left or to the right. If these two amplitudes meet at X, then that tells us that M is moving to the left, right? So the answer to 2.2.4 will be to the left, right? Pulse M will continue moving to the left while pulse L continue moving to the right. The following wave pattern is produced by a transverse wave that takes 4 seconds to complete one vibration. So from that, we know that the period of our transverse wave is 4 seconds, right? And then the first question, 3.1, is saying let's define the term transverse wave. right? So a transverse wave is a wave where the particles of the medium vibrate at right angles to the direction of motion of the wave, right? So as you can see here on the left hand side, the particles are going up and down while the transverse wave moves from A to B, right? So they're moving at right angles to the direction of the motion. So that's the definition for a transverse wave. And then 3.2 says let's determine the frequency of the wave, right? So we've already deduced that the period is equals to 4 seconds, right? Why are we saying the period is equals to 4 seconds? Because we have been told that it takes the wave 4 seconds to complete one vibration. So we can say that the frequency is equals to 1 divided by the period, right? That is just 1 divided by 4, which is equals to 0.25 hertz, right? So the frequency of this wave is 0.25 hertz. And then now off to the next question, 3.3. So 3.3 is saying that if the speed of the wave is 0.05 meters per second, let's calculate the value of x in millimeters. So let's go and look at x, right? So x runs from this point to this point, right? So let's look at x in terms of wavelength, right? So from here, if we keep going to this point, we have one wavelength, right? And then from that point to this point, we have half a wavelength. So we can say that x is equals to 1.5 wavelength, right? We can see clearly from the sketch that x is indeed 1.5 wavelength. So if we calculate the wavelength, then we can just substitute the wavelength here and determine the value of x in millimeters, right? So let's go ahead and do that. We are told that the velocity is equals to 0.05 meters per second. We know that the period is equals to 4 seconds and the frequency is equals to 0.25 hertz, right? So we can say that the velocity is equals to the wavelength divided by the period. So what is the velocity? The velocity is 0.05, and then the wavelength is what we're looking for, and the period is 4 seconds. We can go ahead and cross multiply. So we're gonna have wavelength being equals to 4 multiplied by 0.05, which is equals to 0.2 meters. So wavelength is equals to 0.2 meters, right? So now we can go ahead and say that x will be equals to 1.5 multiplied by 0.2, right? What the wavelength is. And then if you compute that, we should get 0.3 meters, right? But then let's not forget, our question says that we need the value of x in millimeters and not in meters, right? So we're just going to say that x is equals to 0.3 multiplied by 1,000, right? So this should be equals to 300 millimeters. So that's how we essentially solve this kind of problems. And now let's move to the next one, 3.4. 3.4 is saying that how long in seconds does it take for a particle to move from point A to point B, right? Let me show you something. So it takes the particle 4 seconds to move one wavelength, right? So from A up to this point, it takes 4 seconds. So we have the first 4 seconds, right? And then from here up to this point, we take another 4 seconds, right? That's the period of the wave. And then from that point to this point, that's a third 4 seconds. And then from this point to this point, we have half a wavelength. So that is going to take 2 seconds, right? So we have the time we are looking for being equals to the first 4 seconds, the second one, the third, and the 2 for the half wavelength we have at the end, right? So that will be 4, 8, 12, 14. So we have 14 seconds, right? It is the time we take to move from point A to point B, the region of high pressure in a longitudinal wave. A compression is the region of high pressure in a longitudinal wave. That is the answer to 4.1.1. So now we can move to 4.1.2. So 4.1.2 is saying let's use the diagram to determine the wavelength of the wave, right? Let's use the diagram to determine the wavelength of the wave. So how do we determine the wavelength of a longitudinal wave? It is the distance between two compressions, right? The distance between two compressions. So let's go to our sketch and do some analysis. So from this compression here at A to this compression here should be one wavelength, and then from that compression to this compression shall be our second wavelength, right? And from that compression to this region of low pressure here that we have should be half a wavelength. Now we can see that 24 centimeters is equals to 2.5 wavelength, right? So we can go ahead and divide both sides by 2.5 in attempt to find the wavelength, right? And then if we do that, we get wavelength is equals to 9.6 centimeters. So the wavelength of our longitudinal wave is equals to 9.6 centimeters. And then now to 4.1.3, the question says that let's determine the period of the wave if it takes 1.5 seconds for a particle to move from A to B. So it takes 1.5 seconds in order to travel 2.5 wavelength, right? That is the information we have. It takes 1.5 seconds to travel 2.5 wavelength, right? And we want the period. So let's go back to the definition. What is the period? The period is the time it takes to complete one wavelength, right? And then in this question, we're being told that to complete 2.5 wavelength, we take 1.5 seconds. So in order to find the period here, we're going to say 1.5, the time it takes to complete 2.5 waves divided by 2.5, right? And then if we do that, we're going to be able to find the time it takes to complete one wavelength. And then if we compute that, we're going to get 0.6 seconds, right? So the time it takes to complete one wavelength is 0.6 seconds, right? You say the time it takes to complete 2.5 waves divided by 2.5 waves, and then you will get the period. And then now off to 4.2. Two boys conducted an experiment to determine the speed of sound in air. They stood 500 meters away from a mountain, and the boy fired a toy gun directly towards the mountain. And then while the other boy fired the toy gun, another boy simultaneously started a stopwatch. He then recorded the time to hear the echo. The experiment was repeated 3 times and the readings were recorded. Right, and then the first question, 4.2.1, how is an echo produced? An echo is produced by sound waves reflecting off a surface, right? So an echo is produced by sound waves reflecting off a surface. And now 4.2.2. So 4.2.2 says, let's determine the average time for the above readings, right? So we can say that x bar from mathematics is equals to the sum of all x values divided by the number of terms, right? So here we have 3.01 plus 2.95 plus 3.04, right? So we just adding up the time taken for the 3 experiments, right? And then we divide everything by 3 because we conducted 3 experiments. So the average time it took sound to travel to the mountain and back to the boys is 3 seconds. And then let's go and do the next question, 4.2.3. It's saying let's calculate the speed of sound. So we need velocity, right? But then we have the distance. We know that the sound waves travel 500 meters to the mountain and 500 meters back to the point, right? So we can say that our distance is 500 plus 500 because the sound waves travel to and from the mountain. So our distance will be 1000 meters. But what is our time? We just calculated it in 4.2.2, right? Our time is 3 seconds. So here we can go ahead and say that the velocity is going to be equal to the distance divided by the time. And then the distance, that is 1000, and then the time is 3, right? It only takes 3 seconds. And then if you compute that, you're going to get 333.3 recurring meters per second. Right, and now off to the last question, 4.2.4. It says that how does the speed of sound in water compare to the speed of sound in air? Choose from greater than, less than, or equal to. We know fully well that it is greater than, right? It is greater than. That is because water is more dense compared to air. In the introduction of electromagnetic radiation, you should have talked about the fact that it behaves as a wave and as a particle. That is what is meant by the term the dual nature of electromagnetic radiations. It shows properties of both wave and particle. In grade 11, there's a topic on the wave nature of electromagnetic radiation, and then in grade 12, you're gonna explore the particle nature of electromagnetic radiation. Right, let's do 5.2. So 5.2 says that a particle has 3.98 times 10 to the minus 13 joules of energy and has a wavelength of 5 times 10 to the minus 13 meters, right? And then the first question, 5.2.1, says, what is a photon? A photon is a packet of energy in which light travels. A photon is a packet of energy in which light travels, right? Let's move to 5.2.2. 5.2.2 says, what is the speed of a photon, right? If it is a photon, then we know that it's a packet of energy in which light travels. And then what is the speed of light again? The speed of light is c is equals to 3 times 10 to the power 8 meters per second, right? Nothing travels faster than light. And then 5.2.3 is saying that by means of a calculation, let's show that the above particle is a photon. By means of a calculation, let's show that the above particle is a photon. So let's jot down the information we have so that we can see how we can potentially solve this problem. So we're given the energy, right? It is said to be equals to 3.98 times 10 to the minus 13 joules, right? And then we're given the wavelength. It is said to be equals to 5 times 10 to the minus 13 meters. Right, and then the question is saying that by means of a calculation, let's show that the above particle is a photon. How would you know that a particle is a photon? If it's traveling at a speed of 3 times 10 to the power 8 meters per second, you would know that that particle is a photon, right? Nothing travels at that speed except for photons, right? So you're looking for C in 5.2.3. If you can prove that C is equals to 3 times 10 to the power 8 meters per second, then beyond reasonable doubt, we would know that that particle is a photon, right? So let's go ahead and see what we can do here. We know that the energy is equals to Planck's constant multiplied by speed of light divided by the wavelength. Right, and then what is the energy? It is given to us. We have 3.98 times 10 to the minus 13. And then what is Planck constant? 6.63 times 10 to the minus 34. And then multiply by c, speed of light, right? That's what we're looking for. We're trying to prove that it is equals to 3 times 10 to the power 8. If that is the case, then that particle is a photon, right? And then the wavelength, we have 5 times 10 to the minus 13, right? So now the physics is essentially done. We just have to solve for C, right? So let's take it easy. Let's not do any complicated math. Let's just go ahead and cross multiply. So if we do that, we're going to get 3.98 times 10 to the minus 13 multiplied by 5 times 10 to the minus 13. And then this is going to be equals to 1 multiplied by 6.63 times 10 to the minus 34. Everything multiplied by C, right? And then from here on, we're going to divide both sides by the coefficient of C. because we want to isolate C. Is the value of C that we're looking for, right? So we're going to divide the right hand side by 6.63 times 10 to the minus 34. So this number and this one, they cancel out. And then on the left hand side, we have to divide with the same number, right? So that we maintain our equality. So if you put what's on the left hand side on your calculator, you can get 3 times 10 to the power 8 meters per second, because we're looking for speed, and then it's equals to C, right? We can conclude that our particle is indeed a photon because it has a speed of 3 times 10 to the power 8 meters per second, right? Let's move to 5.3 and see what we can do here. So we have 5.3, which is saying, will a photon of ultraviolet light have more energy or less energy than a photon of gamma rays? Let's give a reason. So a photon of ultraviolet light will definitely have less energy, right, compared to gamma rays. We know that gamma rays have the most energy, I think, followed by X-ray and so on. So ultraviolet will have less energy compared to gamma rays. And they're saying we must give a reason, right? We know fully well that the energy is equal to Planck's constant multiplied by frequency. That's another formula we have, right? So we're saying gamma rays have the most energy because they have the most frequency compared to ultraviolet light. So we're going to say less energy because ultraviolet light, right, has less frequency. It has less frequency compared to gamma rays, right? You have to write in full. You don't have to write it like the way I'm doing here. I'm just doing that to save time, right? Or you can even go ahead and talk about the frequency, about the wavelength, I meant, because we know that energy is equal to H multiplied by C divided by wavelength. This might be a bit confusing for a few, but bear with me here, right? You can say that ultraviolet light has less energy because it has a higher wavelength, right, compared to gamma rays, because energy and wavelength, they are inversely proportional to each other. When wavelength increases, energy decreases, right? And the last question, 5.4 says, let's name the type of electromagnetic radiation that is used to study animals at night. That's quite an easy one, right? It's infrared.